All right, this is the ideal gas law video. And so what we're going to learn about is we're going to learn about the ideal gas law. So if you'll turn in your notebooks to your ideal gas law notes, you will see that we have a couple of questions. What is the ideal gas law? What is the ideal gas law equation? How to use the gas law equation? And what is the gas law constant? Our state standard is SC.912.P.12.10, which has to do with amounts of gases. So let's start with ideal gas. An ideal gas, that word ideal means that it's a perfect world gas. So it's not a real world gas, it's a perfect world gas. And so a perfect world gas has a couple of factors. First of all, it has no attraction or repulsion towards other molecules. So those gas particles aren't going to be attracted to, and they aren't going to push away from any other molecules in the container. If it hits the surface, it bounces off with no stick. So it doesn't really change its speed when it hits the side of a container. And then also, if we increase the temperature by applying heat, those particles are going to spread out and they're going to increase in speed. That's just kinetic energy. And then we know, finally, that the ideal gas law is a law, and this law, it relates the amount of gas in moles to the conditions of volume, temperature, and pressure for that gas. So we're going to be looking at four kind of variables here: the amount of gas in moles, and then the volume, the temperature, and the pressure. So you can see here that we have the ideal gas law equation. And the ideal gas law equation is PV equals nRT. Sometimes we say it's the Perv-Nernst equation. PV equals nRT. And then we have listed what each of those variables stands for. So P is pressure, V is volume, N is the amount or number of moles, R is something called the gas law constant, and T is temperature. And so I'm going to go through that equation with you. But let's just kind of review our questions. What is an ideal gas? A perfect world gas with no attraction or repulsion between molecules. What is the gas law equation? That's PV equals nRT. How do you use the gas law equation? We're going to see that in a couple of example problems. And what is the gas law constant? Again, something that we'll talk about in just a second. Okay, so let's look at this ideal gas law. PV equals nRT. P stands for pressure, and that pressure must be in either ATMs or kPa. And that's because of the gas law constant. So we'll talk a little bit more about that in a second, but it must be in ATMs or kPa. V stands for volume, and the volume must be in liters. N is the number of moles of gas, and so again, it must be in moles. R is the gas law constant, and then T is temperature, and temperature must be measured in degrees Kelvin. So let's talk about this gas law constant. There are two different gas law constants, and it depends on the units that you're using in your equation. So if you're using ATM as your pressure, if you're using ATM as your pressure, then you're going to use 0.0821, and we call it Latam Molk, liters times ATM over moles times degree Kelvin. And that is our gas law constant when we're using ATMs as our pressure unit. If we're using kPa as our pressure unit, then we have a slightly different constant. We're going to use 8.3 kPa times liters over MOLK. So that's pressure times volume over the number of moles and the degrees Kelvin. Okay, so anytime I use ATM, my gas law constant will have to be 0.0821. Anytime I use kPa, my gas law constant will have to be 8.3 kPa per liters over moles Kelvin. Remember that in order to get to Kelvin, Celsius plus 273 will give us Kelvin. So if we're given Celsius, we're going to have to add 273 to get Kelvin. And then we also just need to know our pressure conversions, because if we could get different units. If we know that 760 torr or mmHg, remember those are interchangeable, 760 torr or mmHg equals 1 ATM, which is equal to 101.3 kPa, kilopascals, which is equal to 14.7 psi, pounds per square inch. All right, so this is our gas law equation, and so all we have to do is just have to take that equation and we're going to multiply or divide to get the unit that we want. So let's just kind of practice rearranging. So let's say that we had PV equals nRT, and the problem asked us to find the number of moles. So if I was looking for the number of moles, I'd have to move RT over to the side. So the number of moles would equal the pressure times the volume divided by the constant times the temperature. If we were looking for a different situation, let's say we had PV equals nRT, and they were asking us this time to find the volume, then I would have to move pressure over. So I would divide by pressure on both sides. And so the volume would equal the number of moles times the constant times the temperature divided by pressure. And so that's just rearranging using our basic algebra skills. So let's look at an example. And then we're going to look at two examples, and then I think you should have a good understanding of the gas laws. All right, so here are the two examples that I talk about in your notes. So you can refer to the second page of notes where I have these worked out, but I'm going to actually talk through them so you can see what it is that I have done. All right, so question number 1 says the pressure exerted by 111.8 grams of argon gas at a temperature of 85 degrees Celsius is 420 torr. What is the volume of the sample? So I can see, based on my problem, they've given me a pressure, they've given me an amount, they've given me a temperature, and they want to know the volume. So I know I'm going to be dealing with PV equals nRT. So I've got to go through and I've got to see what I'm looking for and then find out what I have. So they ask, what is the volume of the sample? So I'm going to circle volume. In order to get it by itself, I'll have to divide by the pressure. So I know that volume is going to equal the number of moles times the constant times the temperature divided by the pressure. So I'm going to go through and find all of those things. So P, my pressure. My pressure is 420 torr. Okay, but I can remember from my gas law equation that the pressure must be in ATMs or kPa. So I'm going to convert this to ATMs because that's the one that I prefer to use. You could use kPa if you wanted. So I'm going to have to convert that to ATMs. My number of moles, well, my amount is 111.8 grams of argon, but I can't use grams of argon. It's got to be in moles. So I'm going to have to convert that to moles. My volume is what I'm looking for. My R is my gas law constant. And again, I get to pick. Since I'm using ATMs, I'm going to use the 0.0821 liters times ATMs times mole K. If I had used kPa instead, I would have used this one. So I have 0.0821 latam molk. And then my temperature. My temperature is 85 degrees Celsius, but I know I'm going to have to turn that into Kelvin. And that's a quick conversion I can do right here. So I know that I take 85 plus 273, and that gives me 358 degrees Kelvin, but I've got a couple of more conversions that I need to do. All right, so my first conversion is 420 torr. So 420 torr to ATM. Since torr is on top, I put it on the bottom, and I know from my reference sheet that 760 torr equals 1 ATM. So I'm going to say 760 torr equals 1 ATM. So I put that into the calculator. 420 divided by 760 gives me 0.553, and that'll be ATMs. Okay, so now I have my pressure in ATMs, 0.553. I need to turn my grams into moles. So I have 111.8 grams of argon. This is just a gram to mole conversion, so grams of argon in 1 mole of argon. So I've got to grab my periodic table to do that. And I see that argon, there are 39.948 grams in 1 mole using its mass, so 39.948 grams. So I'm going to take 111.8 divided by 39.948, and that's going to give me 2.799 moles of argon. And now I have converted this and I've converted this. So everything's in the right units. Now I just need to set it up into my equation. V equals N times R times T. So I'm going to go ahead and plug that in. So I'm going to say my volume equals N. My number of moles was 2.799 moles times R. We said we were going to use 0.0821 L times ATM over MOL K, and we use the ATM because our pressure unit was going to be an ATM. Our temperature was 85 degrees Celsius, but we converted it to Kelvin, 358 degrees Kelvin. And I'm going to divide that all by P, my pressure, which I converted from torr to ATM, 0.553 ATMs. Okay, so let's take a second and let's look at our units. Our ATMs are going to cancel, our moles are going to cancel, and our Kelvin is going to cancel, leaving us with liters. Is liters a good unit for volume? Yeah. So let's plug it in and see what happens. So we have 2.799 times 0.0821 times 358. I'm going to divide that by 0.553, and the answer that I get is 148.76. 148.76 liters of argon. And that would be my answer. So let's just kind of review what we did. We found out what we were looking for. We made a list of things that we would need. We wrote those things down from the problem, and we made sure that we were in the correct unit. So I had to do a couple of conversions. I then plugged it into the equation that I had rearranged, crossed out units, and was left with an answer of 148.76 liters of argon. Okay, so let's look at the second example. The second example says a helium-filled tank will contain 45 liters of gas if it's held at a pressure of 18.5 psi and 27 degrees Celsius. How many grams of helium are present? Okay, so it's asking for grams of helium. Now, I know that since I've been given a volume, a pressure, and a temperature, I must be using PV equals nRT, but I don't have anything for grams. The closest thing I have for grams is the number of moles. So I'm going to get the number of moles, but then I'm going to have to convert that into grams for my final answer. So in order to get N by itself, I'm going to divide both sides by R and T. So I know that the number of moles is going to equal PV over RT. So I make my list. I'm going to need P, V, R, and T. Okay, so P is my pressure. I have 18.5 psi. I know that's going to be a problem. This time, just for practice, we'll turn it to kPa. We could have turned it to ATM. I just want you to see the conversion when we use it for kPa. Okay, so I'm going to have to turn it into kPa. My volume is going to be 45 liters. R, so I had to choose which gas constant. Since I decided I wanted to try kPa, I'm going to use this, 8.3 kPa times liters over MOLK. 8.3 kPa times liters divided by MOL. Okay, now again, I could have gone to ATM. It's actually an easier conversion, but I just wanted you to see an example where we went to kPa. And then my temperature is 27 degrees Celsius, but I know that that is going to have to be turned into Kelvin. And then I'm going to get the number of moles, but I'm going to have to make a conversion into grams because that's what the problem asked me for. It asked me for the mass. Okay, so let's go ahead and do our conversions so that we can start our problem. First thing we've got to deal with is this PSI, and we're turning it into kPa. So I have 18.5 PSI. Okay, so when I make my conversion table, PSI is going to come down, and I'm turning it into kPa. Well, let's see what it says. We see from our conversions that 101.3 kPa is equal to 14.7 kPi. So 14.7 psi. So 101.3 kPa is equal to 14.7 psi. So I'm going to go ahead and just put that in. 101.3 kPa is equal to 14.7 psi. My psi units cancel, so I multiply across the top, 18.5 times 101.3 divided by 14.7, and I get 127.49 kPa. Okay, so I've dealt with this one. My liters is already in the right unit. I'm using kPa, so I'm matching my pressure units. My temperature, 27 degrees Celsius. Well, I know that's going to have to go to Kelvin, and I do that by adding 273. So 27 plus 273 gives me 300 degrees Kelvin. So that's in the right unit now. So now I'm ready to go. All right, so let's plug it in. We're going to plug in PV over RT. All right, so we know that N equals PV over RT. All right, so my pressure is 127.49 kPa times my volume is 45 liters divided by R, which is going to be 8.3 kPa times liters over MOL times K. And then my temperature is 300 K. All right, so let's look at our like units and see what we can cancel out. I can get rid of liters, Kelvin, and kPa, leaving me with moles, which is what I wanted for N. So that's a double check for us. 127.49 times 45 is going to equal 5737.05 divided by 8.3 times 300 gives me 2490. So 5737.05 divided by 2490 gives me 2.3 moles of helium gas. 2.3 moles. But I know that I'm not done because my problem asked me for grams, and I have this in moles. So I'm going to have to do another conversion. I'm going to have to turn moles into grams, and that's just going to be a simple conversion from the periodic table. So I'll do that right over here. 2.3 moles of helium, He, and I need to turn it into grams. So we know that 1 mole of helium is going to equal its mass on the periodic table, and helium has a mass of 4.003 grams per mole. So I just have to multiply 2.3 times 4.003 is going to give me 21.18 grams of helium. And that should be not the right answer. Let's try that again. 2.3 times 4.003. That looks like a better answer. That makes more sense. So the answer that we get is 9.21 grams of helium. There we go. That makes much more sense. So 2.3 times 4.3, our moles canceled. All right, so that's the ideal gas law. Now you should be prepared to start your worksheet. So go ahead and begin your worksheets.